Hi friends, I welcome you all to this video Matrices in Engineering Mathematics 2. Here I am going to share my ideas, basic application and concepts of eigenvalues and eigenvectors in engineering mathematics. Here I have taken one practical example. From that I explained how we form the system of differential equations and how we solve the equations by ODE method. Then I explained how we transform the same differential equations into matrix form and how we solve the equations by eigenvalues and eigenvector concepts. Most of us have known the basic concepts of circuit. Here I take a parallel inductor-resistor circuit. There are two loops. In loop 1, see this source V equal to E of t. Connect with inductor L1 with 1 Henry. Then the circuit connect with resistor R1 with 2 ohm. Then the circuit closed with source V equal to E of t. The current flow in loop 1 is Y1. In loop 2, there is no voltage rise. The circuit connect with the inductor L2 with 1 Henry. Then the circuit connect with the resistor R2 with 3 ohm. Then the circuit closed with the resistor R1. The current flows in loop 2 is Y2. Now we know that V are equal to I into R, that is voltage across resistor equal to current into resistance. Then the voltage across inductor equal to L into di by dt. Here L is the inductance value. In loop 1, the voltage across resistor R1, that is Y1 minus Y2 into R1, because the current flow in Y1, the current flow out Y2. Therefore VR1 equal to 2 into Y1 minus Y2. Now VL1 equal to L1 into dy1 by dt, because the current flows in loop 1 is Y1, L1 value 1. Therefore voltage across inductor L1 equal to 1 into dy1 by dt. Now we come to loop 2. The voltage across R1, that is Y2 minus Y1 into R1. In this loop, in R1, current flow in Y2, current flow out is Y1. Therefore VR1 equal to 2 into Y2 minus Y1. Now VR2, the voltage across resistance R2, that is 3 into Y2. Now voltage across inductor L2, L2 into dy2 by dt, because current flows in loop 2 Y2. Therefore VL2 equal to 1 into dy2 by dt. By Kirchhoff's voltage law in any closed path, we know that sum of potential rise equal to sum of potential drop, or sum of voltage rise equal to sum of voltage drop. Assume the equations governing its operation with E of t equal to 0 with the initial condition y1 of 0 equal to 1, y2 of 0 equal to 1. In loop 1, we apply KV law. Potential rise E of t equal to potential drop VL1 plus VR1, so that we can get the differential equation dy1 by dt plus 2y1 minus 2y2 equal to 0. In loop 2, there is no voltage rise, so left hand side becomes 0. Therefore 0 equal to the sum of potential drop VL2 plus VR2 plus VR1. Apply VL2 value, VR2 value, VR1 value. We can get the differential equation dy2 by dt plus 5y2 minus 2y1 equal to 0. Now we solve this equation 1 and 2 by ordinary differential equation method. Taking capital D equal to d by dt, equation 1 becomes d plus 2 into y1 minus 2y2 equal to 0. Consider equation number 3. Applying the same, equation 2 becomes minus 2y1 plus d plus 5 into y2 equal to 0. Consider equation number 4. Now solve the equation 3 and 4. By eliminating y2, operate d plus 5 on equation number 3. and multiply 2 on equation number 4. Adding these two equations, you may get d square plus 7d plus 6 into y1 equal to 0. Clearly, the solution is complementary function only. Using the auxiliary equation, m square plus 7m plus 6 equal to 0 by replace d equal to m. Now solve this auxiliary equation, you may get m equal to minus 1 comma minus 6. These roots only called eigen roots or eigen values later. Therefore, the solution of this differential equation is y1 of t equal to c1 into e power minus t plus c2 into e power minus 6 into t, since roots are real and distinct. Using equation number 1, we may find y2. Therefore, y2 of t equal to c1 by 2 into e power minus t minus 2 into c2 e power minus 6 into t. Given the initial condition y1 of 0 equal to 1 and y2 of 0 equal to 1, we may substitute in this above two equation. We may get y1 of t becomes c1 plus c2 equal to 1. y2 of t becomes c1 by 2 minus 2c2 equal to 1. Simplifying this, we can get c1 equal to 6 by 5, c2 equal to minus 1 by 5. Therefore, y1 of t and y2 of t comes like this. Also, we can write y of t in this matrix form. We can obtain the same current value y of t by using eigenvalues and eigenvectors, so that we rewrite the equations 1 and 2 for transforming into matrix form, so that equation 1 becomes dy1 by dt equal to minus 2y1 plus 2y2, equation number 5. And equation 2 becomes dy2 by dt equal to 2y1 minus 5y2. Consider equation number 6. From equation 5 and 6, we can write dy of t by dt equal to capital A into y of t. Consider equation number 7. This is required matrix form of this above differential equation. Y of t is nothing but y1 of t, y2 of t. These are current in loop 1, current in loop 2. Capital A is the square matrix, row wise minus 2 to 2 minus 5. Now we solve the equation 7 with the square matrix A. From the previous method, the solution may be assumed in the form y of t equal to x into e power lambda t. X is the column vector. Substitute this equation in equation number 7. We may get d by dt of x into e power lambda t equal to ax into e power lambda t. After the differentiation with respect to t, we may get lambda x into e power lambda t equal to ax into e power lambda t. Simplifying this one, we may get ax equal to lambda x. This is the important one. This leads to the definition for eigenvalues and eigenvectors. Let A be a square matrix and x be a non-zero column vector. Then there exists a scalar lambda such that Ax equal to lambda x. Here x is called as eigenvector corresponding to the eigenvalue lambda. Now we see the procedure to find the eigenvalues of the matrix. See, take the matrix A of order n. Second, form the characteristic equation, determine A minus lambda I equal to 0, where I is the identity matrix of order n. Expand, determine A minus lambda I equal to 0. It comes lambda power n minus trace of A into lambda power n minus 1. Third term, sum of principal minus of order 2 into lambda power n minus 2. Minus sum of principal minus of order 3 into lambda power n minus 3 plus up to minus 1 power n, determinant A equal to 0. Look at all the terms are alternate sign. Now we see the simple form of characteristic equation. For 2 by 2 matrix, lambda square minus trace of A into lambda plus determine A equal to 0. In simple form, lambda square minus s1 lambda plus s2 equal to 0. There we assume s1 equal to trace of A and s2 equal to determined value of A. The same way, the characteristic equation of 3 by 3 matrix lambda cube minus trace of A into lambda square plus sum of principal minus of order 2 into lambda minus determine A equal to 0. Here lambda cube minus s1 into lambda square plus s2 into lambda minus s3 equal to 0. There we assume s1 equal to trace of A, s2 equal to sum of principal minus of order 2, s3 equal to determined value of A. Now let us see the procedure to find the eigenvectors of the matrix. Take A minus lambda I into x equal to 0 and assume the eigenvector x equal to x1, x2, x3 up to xn. Substitute the lambda value and derive the system of equations using cross multiplication method to get eigenvector x. From the equation number 7, to find the eigenvalues of the matrix A, row wise minus 2, 2, 2, minus 5. Therefore, the characteristic equation of 2 by 2 matrix is lambda square minus s1 into lambda plus s2 equal to 0. Here, s1 equal to trace of A, that is sum of principal diagonal elements of matrix A, that is minus 2 minus 5 equal to minus 7. s2 equal to determined value of A. So answer 10 minus 4 equal to 6. Therefore, the characteristic equation of A is lambda square plus 7 lambda plus 6 equal to 0. Factorize this one. Lambda plus 1 into lambda plus 6 equal to 0. Solving this one, lambda equal to minus 1 into minus 6. Therefore, the eigenvalues of the matrix A is minus 1 comma minus 6. Now, to find the eigenvectors of the matrix A corresponding to the eigenvalues lambda equal to minus 1 comma minus 6. Now we take the corresponding equation A minus lambda I into x equal to 0. Assume the eigenvector x equal to x1, x2. Now we substitute the eigenvalue lambda equal to minus 1 in the above equation. Therefore, we may get the square matrix minus 1, 2, 2, minus 4 into the column matrix x1, x2 equal to 0, 0. Simplifying this one, we may get minus x1 plus 2x2 equal to 0 and 2x1 minus 4x2 equal to 0. Here, the two equations are looking like different, but both equations represent x1 minus 2x2 equal to 0. Here, there are two unknown, but we have only one equation x1 equal to 2x2. Therefore, assume any arbitrary constant. Taking x2 equal to 1, we get x1 equal to 2. Therefore, eigenvector corresponding to lambda equal to minus 1 is x1 equal to 2, 1. Substitute lambda equal to minus 6 in this equation, we may get the square matrix 4, 2, 2, 1, column matrix x1, x2 equal to 0, 0. Simplifying this one, we may get 4x1 plus 2x2 equal to 0, 2x1 plus x2 equal to 0. Both are looking like different, but both the equations represent 2x1 plus x2 equal to 0. The same way, there are two unknowns, but we have only one equation. Assume any arbitrary constant. x1 equal to 1, we may get x2 equal to minus 2. Therefore, eigenvector corresponding to lambda equal to minus 6 is x2 equal to 1 minus 2. Now we conclude the eigenvectors of the matrix A are 2, 1, 1 minus 2. From the equation 8, the solution current flows in loops is described by y of t equal to x into e power lambda t, where x is an eigenvector corresponding to eigenvalue lambda. Therefore, the current flows in loops are y1 of t equal to 2, 1 e power minus t, y2 of t equal to 1 minus 2 into e power minus 6 into t. By the theorem, eigenvectors corresponding to distinct eigenvalues of square matrix are linearly independent. Using the above the theorem, we can write the general solution as linear combination of these vectors. That is, y of t equal to a into y1 of t plus b into y2 of t. Therefore, y of t equal to a into 21 e power minus t plus b into 1 minus 2 e power minus 6 into t, where a and b are arbitrary constants. Given initial condition y1 of 0 equal to 1 and y2 of 0 equal to 1. Applying this initial condition in the above equation, we get this equation. Simplifying this one, we can get two equation 2a plus b equal to 1 and a minus 2b equal to 1. Solving these two equation, we get a value equal to 3 by 5 and b value equal to minus 1 by 5. Substitute these arbitrary constants values in this y of t equation, we get like this. Simplifying this one, we get y of t equal to 1 by 5, the square matrix 6 minus 1 3 2 and column matrix e power minus t e power minus 6 into t. This is the same result what we have obtained through ordinary differential equation. Hope you understood how the ordinary differential equation and matrices helps to find the current values in circuits. Meet you in next video, properties of eigenvalues and eigenvectors and some problems based on these properties. Thank you friends for spending your valuable time to watch this video. If you like this video, share and subscribe.